All right, folks, hello. Let's take care of section 11.2. We're looking at series. So I'm going to have lots of examples here. It's going to be in two parts. Excuse me. So you're going to also practice some of these as we go. All right, so the series is the sum of terms of a sequence. An infinite series, or just plain series, if you just hear that word, means that we're going to add up all the terms of our sequence out to infinity. So a sub 1, a sub 2, a sub 3, a sub 4, the first four terms of your sequence, we're adding those together. All right, so those are the terms of your series. We can have finite series or partial sums. This is where we now, instead of having infinity at the top of our summation, we have a definite constant value and we stop at some point. These are called partial sums. So capital S sub 1, this is the sum of the first term. S sub 2, the sum of the first two terms. S sub 3, the sum of the first three terms. Fourth terms, five terms, so on and so forth. Those are partial sums. Now, partial sums themselves will form a sequence. So the sequence of partial sums, here's your sequence function notation. Capital S sub n is equal to the first partial sum, second partial sum, third partial sum of the sequence terms. Now, if your partial sum sequence function converges to some value, let's call it lowercase s, then that original series that we looked at also converges to that sum of s, and that little s is called the sum of the series. So by definition, again, you can read through this, it's in your notes, or you can pause this to write it all down. It's basically explaining all that using the author's notation. All right, so if the sum of this series is s, then we know it converges, and if it's s sub n is divergent if it goes to infinity. Okay, and a good test for that is using limits. So example 1, applying the previous definition, follow the steps. Write out a few terms of your sequence. So there's my definition, and using this sequence function, turning it into a summation. N is equal to 1, 2 times 1 is 1, minus 1 is 1. Well, it's linear, so I'm going to count by 2s, 1, 3, 5, 7, add those together to 2n minus 1, and so on and so forth out to infinity. Now let's find a few partial sums. Let's say the first four terms here. So s sub 1 is 1, s sub 2, second partial sum is going to be 4, third partial sum, 4 plus 5, 9, fourth partial sum, 1 plus 3, 5, and 7 is 16. I'm starting to see a pattern. The fifth partial sum, just to double check, yep, my pattern was 1 squared, 2 squared, 3 squared. I started to notice perfect squares when I got to 16. So there is my sequence formula for my partial sum sequence. All right, so then take this new sequence formula for your partial sum and apply the limit as n approaches infinity. Well, wait a minute, that's going to go to infinity. Infinity squared is still infinity. Well, what that means is that this is divergent. It diverges. The limit doesn't exist. So if it doesn't exist for this, then it's sure not going to exist for the original sequence function 2n minus 1. That's also going to diverge. All right, so if the limit as n approaches infinity of our partial sum sequence is equal to that little s we said, then that summation of the original sequence is going to converge. And that little s, that is going to be the sum of your series. If we get positive or negative infinity for our limit, then everything diverges, even the original sequence function. All right, example 2. Determine if this infinite series for a sub n equals 1 over 2n converges or diverges. All right, let's write out some terms. N is equal to 1, so 2 to the first, 2. 1 over 2 squared, 4, 1 over 2 cubed, 8, 1 over 2 to the fourth, 16, so on and so on and so forth. All right, find some partial sums. 1 half plus 1 fourth, 3 fourths, 1 half plus 1 fourth plus 1 eighth. S sub 3, third partial sum would be 7th, 8th. I'm starting to see a pattern here. My guess would be, let's see, 16. I'm going to say 15 over 16. Yep, there it is. I noticed that the numerator was one value less than the denominator. So if we went to, let's see, what's that, 2 to the 5th is 32, I'm guessing s sub 4 would be 31 over 32. All right, so yes, this also makes a sequence function out of your partial sums. And this is 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, so that's 2 to the nth power. And again, because this is 1 less on the top, that'd be 2 to the n minus 1. Great! We have this partial sum sequence formula. Apply the limit to it. Well, since we have this ugly looking fraction, it's probably best if we separate it. Since we have one term in the denominator, make two fractions. 2 to the n over 2 to the n minus 1 over 2 to the n. And I think you can see what's going to happen here. Cancels to a 1. 1 over infinity, 0. 1 minus 0, yep, is 1. So that means your original summation up here is going to add up to a value of 1. It's going to converge as well. All right, sometimes step 3 is very difficult and we can get stuck. There are other methods to help us. Often we are given S sub n so we don't have to find it. Sometimes you might recognize some special series, say geometric and telescoping, whose sums are really quick and easy to find. So we know that a geometric series from college algebra, an infinite series, an infinite summation of a geometric sequence has this special formula right here as long as your R is less than 1, its absolute value. I like to say between -1 and 1, 6 of one, half dozen the other. And if it's equal to or greater than 1, then it's divergent. Okay, so you got to be careful here. Watch where your n's are starting because there is a slight trick here. A lot of times these formulas, see this a right here, that's your first term. So you see this number being multiplied to your r to some power. Everyone sometimes thinks that's your first term. It may not be. All right, so you got to watch that. You may have to plug in this value here into the formula to actually find the first term a. All right, so my previous example, that 1 over 2 to the n, we can write 1 as to the n power as well. So that makes it 1/2 to the n power. 1/2 is less than 1. So therefore it's a geometric series. It's going to converge. And like I said, I like to write my formula as a sub 1. That reminds me to find the first term if necessary. So my infinite series is equal to a sub 1 over 1 minus r. So here I got to put the 1 in for n, and that's 1/2. Notice that what number's in front of your parentheses is a 1. That's not the first term. But if you looked up here, you may have thought, oh wait, that's a 1 out there. That's what I'm going to put here. No, you sometimes have to plug that in. 1 minus 1/2, that's going to be 1/2 over 1/2 equals 1. That's the sum of that series, which we saw earlier was 1 as well. All right, so here we have an example of a sequence, and we were trying to find this. It's going to add up to be infinity. So what we need to do is we need to turn that into a summation problem so I can tell if it's a geometric series or not. Okay, so 3 minus 4 plus 16 thirds minus 64 over 9 plus, it's alternating. So again, remember back when we did these before, this is when n is equal to 1, we get a 3. When n is equal to 2, we get a -4 or -4. When n is equal to 3, we'll get 16 thirds. When n is equal to 4, 64 over 9. I see base 4 numbers on the top. 4 to the first, 4 squared 16, 4 to the third is 64. So back up the boat, subtract 1. When I have this 3 here for my first term, that means I have 4 to the 0 power. That's a 1. That's why there's no 4 as a factor in this problem. In the denominator, I see base 3 numbers. 3 to the first, 3 squared. Back up the boat. Subtract from the powers. This is 3 to the 0. 3 to the -1. So to write my sequence function, when n is equal to 1, I need a 0 for a power. When n is equal to 2, I need a 1 for a power. So I see this as 4 to the n minus 1 power. On the bottom, I see when n is equal to 1, I need to be at -1. When n is equal to 2, I need to be 0. When n is equal to 3 for the third term, I need a 1. I'm subtracting 2 from my n. So I see 3 to the n minus 2 on the bottom. Well, since our signs are alternating and your first term is positive and 4 is raised to the 0 power, which is going to be a +1, let's put the negative on the 4. So there is my sequence function. Now that I have the function, I can write it with the summation notation, but my powers are not the same. So I'm going to take out a 1 here. So I can make this into n minus 1, which means I need to multiply a 3 to the first power, because when you multiply like bases, I'll add that 1 to the minus 2, making it into a minus 1. So there you have it. All right, powers are the same. Great. Now there's your leading coefficient, 3, on your base, r, which is going to be negative 4/3 to the n minus 1. Wait a minute. R is a negative 4/3. Take its absolute value. That's a positive 4/3. That's greater than 1. It diverges. We're done. We don't need to continue. We're not going to find the sum because it doesn't exist. All right, off to the next problem. Okay, so here, very similar to what we saw, that 2 to the n. Now it's a square root of 2. So I'm going to let you get this one started. So pause the video. Work on it yourself. Okay, we're back. All right, so you should have had 1 over the square root of 2, all to the nth power. That's your r. Find its true value. It's approximately 0.7. It's less than 1, so it's going to converge. You can use that formula. First term. Okay, n is 0. We put 0 in here. This cancels all out to a 1. My r, 1 over the square root of 2, so 1 minus 1 over the square root of 2. Let's do some simplifying. Get rid of that radical 2 in the denominator. Multiply top and bottom of, if you will, the blue fraction by the square root of 2. Top and bottom, that's going to make that square root of 2 over the square root of 2 minus 1. Okay, we could take this a little further and rationalize this by multiplying by its conjugate, square root of 2 plus 1. That will give you 2 plus the square root of 2 on the top. Square root of 2 times the square root of 2 is 2. Negative 1 times 1 is negative 1. We know the middle terms cancel. That simplifies to 2 plus the square root of 2. Okay, so there's the sum, because this converged. Example 5. Okay, again, I'm going to let you start this one. So hit pause, watch that negative power. I would say make it a positive. All right, so pause and work it out yourself. Okay, great, we're back. All right, so make that a positive power, so that's 1 over e to the nth power. So there's your r. 1 over e is approximately 0.37, which is less than 1. This is converges, so we can use this formula. Let's plug everything in, but notice, I hope you check this, n is equal to 2, so I got to put that in first, so I get 1 over e squared times 5. So 5 over e squared is my first term, all over 1 minus r, which is the 1 over e. How many people just put a 5? Okay, erase, or make a little slash, make e squared in the denominator of the top. All right, let's work this out. We want to get rid of those two denominators. E to the second power is the biggest possible, if you will, the LCD of both of those individual fractions. Multiply e squared, top and bottom. Do some canceling. We get 5 over e squared times 1 is e squared. Cancel e minus e. That's a good answer, or you can factor out an e. Both are good to me. All right, great. Okay, here we go. Start this one on your nose. Get the powers the same. Pause. Okay, we're back. Okay, 7 times. Okay, got to break off that plus 2. So remember, when you multiply like bases, add powers. So that's 5 to the n times 5 squared. Move that out to the front. That's 7 over 5 squared. Now your 2 to the n over 5 to the n is now 2 to the fifths to the nth power. That's geometric. Your r is 2/5. That's less than 1. It converges. Again, notice what n starts with. We have to come up with our first term. It's ugly. 7 over 5 squared times 2 to the third power is 8. 5 to the third power in the bottom. I didn't multiply that out because I think what I'm going to do here is multiply by 5 to the fifth power, top and bottom. So here's your 1 minus r on the bottom, 1 minus 2/5. So multiplying by 5/5, top 5 to the fifth power, top and bottom, cancels the numbers. 7 times 8 is 56. 5 to the fifth, that's times 1. Minus 2 times 5 to the fourth. Calculator tells me 56 over 1,875. Done. Okay. 7. Well, this is a repeating decimal, and I'm going to set this up as the previous problem. I'm going to create it as a summation. Okay, so the first time I see repeating decimals is right here. So this is technically 75 over tenths, hundredths, thousandths place, 10 to the third. Then the next 7/5 is over 1, 2, 3, 4, 5, 10 to the 5th power. Then the next plus 75 is 10 to the 7th. So that will continue on. 75 over 10 to the 9th, 75 over 10 to the 11th. We can factor out a 75, and we can factor out a 10 to the 3rd from all your terms. So now this is when n is equal to 1. So we can have n minus 1 plus, here we have 1 over 10 squared. So I must have multiplied to the 1 a 1 over 10 squared. Multiply by another 1 over 10 squared, I get 1 over 10 to the 4th. So that 1 over 10 squared is my r. It's to the 0 power here, to the first power in the second term, and to the second power on the third term. So that's my n minus 1 for the exponent. This is when n is 1, n is 2, n is 3, 1 less on those powers. There's my r, definitely less than 1, so it's going to converge. Apply your formula. Now because we have n minus 1, and this was truly your first term of 1, then 75 over 10 to the 3rd is your first term, a sub 1. Over 1 minus 10 squared, again, let's multiply by 10 to the 3rd. Do some canceling, 75 over 10 to the 3rd times 1, 10 to the 3rd. 10 squared cancels in there, leaves me a 10 times the 1 minus 10. Calculator gives me 5 over 66. All right, pause.